We just saw how unbounded dependency constructions, like WH questions and relative clauses, were problematic for the most naive or basic applications of context-free grammars as a formalism for natural language structure. Originally, in the dawn of the cognitive science of language and generative grammar, this kind of construction played a crucial role in motivating transformational grammars that were more powerful than context-free grammars. But it turns out that context-free grammars actually can account for these constructions with the right approach, and we're going to see that now. What we're going to use is a meta-rules approach following the innovation in the 1980s of generalized phrase structure grammar, which is sometimes called GPSG. And we're going to require the following meta-rules, which are constraints on the composition of the sets of non-terminal categories and rules in the grammar. First, we're going to designate a basic set of non-terminal symbols, which we'll call NBasic, and a basic set of non-terminal rules, RBasic. And these will both be subsets of the total set of non-terminal symbols and rules. So this is just a constraint on the inventory of these rules. Second, given that designation, we're going to say that for every category pair in the basic category set, in the basic non-terminal set, there must also be a derived non-terminal category, a derived non-terminal symbol. And if the category pair in the basic set is x and y, then there must be a derived category of the form x/y that is also in the non-terminal set. And the interpretation of that category is as follows. It is an x that is missing a y inside. So it's an ordinary x, but it's just missing a y. And this is not something additional that we have to stipulate. This interpretation is going to be an emergent property of what happens when we apply the meta rules to form the entire grammar. Third, we go to derived rules. For every basic rule in the grammar and every basic category in the grammar, then if the basic rule is of the form x goes to alpha 1 alpha n, then for every possible one of those alpha sub I, there's going to be a derived rule in the grammar, which has on its left-hand side x/y. Remember that x came from the basic rule's left-hand side, y came from the basic category set, and we know that x/y is already in the grammar as a category due to meta rule number 2. And then this adds a collection of derived rules. And what you can think about this as being is it's saying that there is a derived category that can go to what the basic category version of that category would have gone to, except that the missingness of y is propagated down into one of the children of the derived category. And that creates a collection of derived rules that will propagate information about missing elements throughout the different parts of trees. And then finally, there's a last part, which is that for every basic category x, there's another rule in the grammar, which is of the form that x which is missing x, that is, an x which is missing itself, rewrites as the empty string. Okay. So that's the ultimate set of constraints that the meta rules constitute. So let's see this in action. What I have here in the upper left is just a recapitulation of the meta rules with just some coloring. So the basic set is green, and then more importantly, I'm going to mark out derived rules in purple. Okay, so let's start off. So we have the basic categories, we're going to say, in this rule set are the categories S, NP, VP, and Comp C. Comp C is for complement clause. You'll see this elsewhere in general in these slides and lectures as S bar. And the basic categories are just these. And then we have the basic rule set, which is in the upper right. Now, let's start with meta rule number 2 and meta rule number 3. Meta rule number 2 will add some derived categories. Meta rule number 3 will say what the rules that rewrite those derived categories will look like. And then we'll add meta rule number 4, which is the rewrite rule of a category that's missing itself goes to the empty string. And I'm not going to show you, there's many meta rules and new rules, derived rules, and new categories that will arise. We actually only need to attend to a small subset of them to see where the crucial action is in this grammar. The derived categories that we're going to care about are going to be the ones where S is missing an NP, VP is missing an NP, NP is missing in NP, that is, an NP is missing itself, and then a complement clause is missing in NP. And there are going to be corresponding derived rules, and these are in this box that I give on the right. And so what you can see is that, importantly, for example, an S that is missing in NP can rewrite in any of two ways. We start with this basic rule, S goes to NP-VP, and so NP is the target category Y in meta rule number 3. X goes to alpha 1, alpha n is identified with the S goes to NP-VP rule. And so for every I in 1 through n is equal to 2 because there are two daughters of S goes to NP, there has to be a rule that is going to be S/NP goes to what S would ordinarily go to, except that the ith daughter is missing in NP. So when I is equal to 1, we get that the NP, the first daughter of S, is missing in NP. And when I is equal to 2, we get that the second daughter of S, the VP, is missing in NP. Okay. And we're going to apply that also as well, for example, to the VP rule. And I'm not giving you an exhaustive set of the VP/NP rewrites, but these are the relevant ones, likewise with the comp clause/NP rule. We get all of these derived categories. Okay, and this is going to turn out, you'll see on the next slide, that this actually gives us all of the right behavior if we just do one additional thing, which is that we actually change the specification of what the relative clause rewrite rule is from what it originally had been. Originally, we had said that a relative clause rewrites as that S. And we changed that rule to say that actually the relative clause introduces a derived category, not a basic category. What derived category does it introduce? An S that is missing in NP. From a functional point of view, a relative clause is a modification of a noun. And that noun that is being modified plays the role inside the relative clause's S category that would ordinarily played. And since that role is already being played, that NP is missing. And so we'll see how that works in the next slide. So I have on the top exactly the same grammar, and this is just a specification of an analysis of the relative clause. The rock that the squirrel likes can be found in the garden under this grammar. So what we have here is the rock, and I've elided the full details of this VP just for simplicity. Everything is as it was before, but what's crucial now is notice that once again, RC, relative clause, rewrites as that SNP. And that SNP, S/NP, that /NP is propagated down through the chain of tree nodes because now we're rewriting a derived category, not a basic category. So we use the S/NP goes to NP-VP/NP at this level. And then we use the VP/NP goes to NP/NP at this level. And now we have an NP/NP, and now we use this empty rewrite, which has been introduced as a new derived rule, to finally rewrite NP/NP. And crucially, that does exactly what we need, which is to say that nothing appears as the object of likes, because it's in an environment where there should be an NP missing, and the NP that turns out to be missing is the one that is the object of likes. And I'll leave it as an exercise. You could actually have used this in another way to actually have the subject of the relative clause missing rather than the object of the relative clause. All that still follows just from the same grammar. Okay, so that's example number 1. It turns out that this not only works for those simple examples, but it also allows us, as we saw earlier, to make a relative clause an unbounded dependency construction. The missingness of the noun phrase can be propagated down arbitrary levels of tree depth. So for example, this is an analysis of the sentence, the rock that the squirrel thinks that the dog likes can be found in the garden, which you probably recognize as a perfectly well-formed sentence of English. And if I had an object after likes, it would be bad. So if I said, the rock that the squirrel thinks that the dog likes the tree can be found in the garden, that would be bad. The tree is like a superfluous element. The reason that this works is that we have a chain of rules that work to propagate this missingness of an NP. RC rewrites as that SNP here. SNP rewrites as NP VP/NP here. VP/NP rewrites as V complement clause/NP here. Complement clause n/np rewrites as that, snp, s/np here, and then the rest is as you saw on the previous slide. And you can probably see that I could repeat this kind of embedding here, where I rewrite as a VP and then I apply a verb phrase rewriting with a complement clause that's missing an NP any number of times that I want. And so actually this would allow me to propagate this missingness of an NP arbitrarily far down. It also works, it turns out, with nested relative clauses. So here is our example, which was a continuation of this multiple center embedding. The rock that the squirrel that the dog chases likes can be found in the garden. And here what you see is that there are two instances of a relative clause rewrite rule. In this case, actually, the slashes don't interact with each other. So the missingness of an NP is resolved in this part of the tree, and the missingness of an NP here is resolved in this part of the tree. So the local information is kept in the right parts of this hierarchical structure. Okay. So at this point, we've seen that actually context-free grammars do give us a means of handling unbounded dependency construction, as long as we require the right structure within the context-free grammar formalism. And what I want to emphasize is that we have not gone out of the space of context-free grammars. In fact, what we've done is we've gone into a subspace of the possible context-free grammars by requiring certain conditions on what sets of categories and rules co-occur in a grammar. And so unbounded dependencies are actually within the means of context-free expressive capacity, at least the kinds of unbounded dependencies that we've seen so far. So we'll take a quick break, do a quick summary of some points that we've learned about various types of English syntax, and then we'll go on with some more general remarks about formal language theory and context-free grammars and beyond.